In this video, we will discuss the concept of stability. In chapter 1, we mentioned that stability is the basic and absolute requirement for a control system. Then, what is stability? There are many different definitions about stability depending on the kind of system or point of view. So here we will limit ourselves to linear time invariant systems. We will discuss two definitions of stabilities from two different perspectives. The first definition of stability is discussed from impulse response. Then the second stability is discussed from the input-output relationship. Then first, let's look at the stability from impulse response. A system is stable if the impulse response approaches zero as time approaches infinity. Impulse response is also called the natural response. It is a property of the system itself. A system is unstable if the impulse response approaches infinity as time approaches infinity. A system is marginally stable if the impulse responses neither decays nor grow, but remains constant or oscillate. From the impulse response perspective, we have the definitions of stable, unstable, and marginally stable, depending on the impulse response of a system. Since the transfer function is the Laplace transform of the impulse response, then we can determine the stability from the transfer function. Then how to determine the stability? Let us first learn two concepts about transfer functions: poles and zeros. For linear time invariant systems, the transfer function is a rational transfer function. It can be written as a ratio of two polynomials. The denominator polynomial n and the numerator polynomial n and the denominator polynomial d. For each polynomial, it is a polynomial of a complex number, complex variable s, b here, and a here. They are real variables. For any physical systems, the order of the denominator polynomial is always greater than or equal to the order of the numerator polynomials. That is, n is always greater than or equal to m. When we discuss the variable s in the complex plane, then we can factor out the numerator polynomials and the denominator polynomial. Here, k is the same with b1. We call it transfer function gain. Di, they are zeros of the numerator polynomial. Pi, they are pole. We call it, they are the roots of the denominator polynomial. Zeros are the roots of the numerator polynomial. They determine the transient performance of a control system. Pi are the roots of the denominator polynomial. They determine the stability. By determining the mode of the system. We know the transfer function is the Laplace transform of impulse response. If we think the Hs is the output when the input is impulse signal, then we can use partial fraction expansion to calculate the time response. Then we know the pole here, they can determine the mode, that is exponential terms. And the zeros, they can determine the site. So they determine transient performance. Let's consider the transfer function in the zero pole form. So let's discuss in two different cases. First, let's assume if the PI real or complex but distinct. In the poles in the denominator, if any of the PI, they are a single pole, then we know when we do the partial fraction expansion, the sum will have a term Ci over S minus Pi. If we apply inverse Laplace transform, we will get Ci times exponential PIT. Then, based on the definition of stability, we will see if this term will decay to 0 or grow to infinity. If all terms decay to 0, then we know the system is stable. If any of the term grow to infinity, then we know the system is unstable. It's interesting to think of the complex pole. So if a PI is a complex number, then it will oscillate. Now let's think of this case. If any of the poles Pi are real or complex but repeated. We did not discuss this case in the class, but I can let you know that we can still use partial fraction expansion. The only difference from the single pole is that in the partial fraction expansion, so the Ci coefficient need to multiply by T for repeated pole Pi when we do the inverse Laplace transform. So then here is very interesting to see when the pole in the imaginary axis then it will grow unbounded. Based on the definition, the system is stable if its impulse response decays to 0, and it's unstable if they diverge. Now let's look at this figure. It shows the time response associated with the location of the poles. If the poles are in the left half plane, then we see the impulse response decays to 0. Like in this case, we have a complex pole. And here we have 2 real poles. However, if the poles are in the right half plane, then we see they will grow to infinity. It's interesting to look at the poles in the imaginary axis. For single poles at the origin, we know the time response is a constant. If they are imaginary numbers, then they will oscillate. Here, there are only the response for single poles. But for repeated poles, as we discussed before, we need to time t in front of the time response. For example, we have here, we have repeat poles of A, J. Then the time response is a sine function, but times by t. Eventually, it will diverge to infinity. Same here. Therefore, we know if a system is stable, if and only if every term exponential pi t convert to 0. For single poles. For all pi as t approaches infinity. It must be true for all poles. Therefore, we know the pole pi must, the real part must be less than 0. In other words, they must be in the left half of the S-plane. Here, 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 or here. For repeated poles, if we change Ci by Cti, it will still decay to 0. Even for repeated poles. if they are in the left half plane. Then stability basically means all poles strictly in the left half plane. Unstable, any poles in right half plane. For neutrally stable, if for unrepeated poles, for J omega, it is called neutrally stable because the time response will be oscillate. It will neither decay or nor grow. If any pole, zero pole, it is still neutrally stable. The time response is a constant. Now let me give you a few minutes to think about what about we have repeated J omega poles. For example, we have two poles at the same locations. In this case, is the system stable, unstable, or neutrally stable? Neutrally stable can also is the same with marginally stable. Just different names. Let me give you 1 minute to think about so if we have repeated J omega poles, the time response will be T exponential plus minus J omega T. So it will be T sine omega t plus or minus j cosine omega t. Then as t approaches infinity, the time response will approaches infinity. Therefore, it is unstable. Then how about repeat pulse at zeros? We have repeat pulse, two of them at zeros. So it will be 1 over s squared in the transfer function. Again, let me give you 1 minute to think about the system with 1 over s squared. It is stable, unstable, or marginally stable. It is also called neutrally stable. Then if we apply the inverse Laplace transform, then it will be time response is t. As t approaches infinity, it will be the time response will be infinity. Therefore, the system is unstable.